Okay, so today we have Dr. Robert Liang. I'm here to present the results presentation for enhancement of UASLOPE for improving implementation efficiency. What we'll do is, if you have any questions and you're watching the webinar, go ahead and type them into the chat pod as the presentation is going on, and then at the very end we'll give you a chance. We'll go over the questions and have him do a Q&A. After the presentation's over with, you'll be able to find the presentation on the research website, and if you have any further questions, feel free to go ahead and email the research team. And without further ado, I will hand it over.
Okay, thank you very much. Good afternoon. Today I'm very happy to come to central office to make a presentation on a recently completed project for enhancement of a software program called UASLOPE that was developed earlier for the purpose of designing a drill shaft for stabilization of unstable slopes. And the scope of this work is to improve the earlier version of the UASLOPE to help the engineers to use the program easily and to enhance their design optimization process by implementing some of the useful features. So today I'm going to talk about the background of this project and then highlight a little bit of the earlier version of the UASLOPE 2.1, and then talk about the current work that was just completed in terms of the different aspects of the enhancement to the program. And then I will show you the example using the new program to strategy to optimize the design of the drill shaft. Also, we'll bring out some of the other versions of the UASLOPE that was not part of this project, but was published in some other journal publications. And finally, I will summarize the work. So to begin with, let's look at the issues related to the design of drill shaft for the purpose of stabilizing unstable slope. And so idea is that the drill shaft provides relatively steep inclusion in otherwise unstable soil mass. So this rigid inclusion can be constructed nowadays with a variety of construction methods, since the construction method for drill shaft have been well advanced, so that the drill shaft can be constructed in almost any kind of soil formations into the rock. So the construction method can be adaptable to very difficult terrains and different types of soil conditions. Furthermore, drill shaft is considered to be a permanent structure, so the issues related to the degradation of the structural elements over the time will not be an issue. So more often than not, the drill shafts have been used by DOTs as one of attractive alternatives for stabilizing unstable slope compared to other methods of stabilization or remediation. But the design of drill shaft for stabilization of unstable slope actually entails two important tasks. One is how to evaluate the factor of safety of the slope with this rigid drill shaft inclusions. So that's one of the very important geotechnical considerations, and a methodology for evaluating the factor of safety with drill shaft on the slope needs to be developed. The other aspect of the design relates to the design of the drill shaft as the structure member so that the drill shaft can withstand the load transfer from soil mass to the drill shaft as a structure member, and so therefore the strength capacity of the structure member and the serviceability of the drill shaft need to be evaluated and designed for. So those are the two important design issues when one encounters the problem of trying to use the drill shaft to stabilize on unstable slope. So now, in terms of the first issue related to the methodology to evaluate the factor safety, well, the drill shaft has been installed into the slope. There are basically two schools of thought in terms of how to realize the benefit of the drill shaft in improving the factor safety of the slope. The traditional way is shown on the top, which are labeled as others. Basically, when you evaluate the factor safety of slope, we're looking at the strength available from soil mass, which is called the resistance available, and divided by the driving force, which is the gravity-induced force that's driving the soil mass downslope. So in the traditional approach, most people consider the drill shaft as a structural element to contribute to the resistance. So you can see we add whatever the resistance that one can attribute it to the drill shaft to the resistance side. Therefore, the factor safety of that slope reinforced with the drill shaft will be increased because we have additional strength or resistance to the sliding coming from the drill shaft. But the question is, how do you calculate that contribution from the drill shaft? There are people using the strength of the concrete as an additional shear strength, which seems to be very, very conservative because the strength of that drill shaft can be very large. And in that approach, we often ignore the spacing effect or three-dimensional effect of the drill shaft. The drill shaft is not functioning as a wall, actually a space apart. So there are disadvantages and some issues related to that sort of school of thought. But in the UASLOPE computational algorithm, we kind of look at it as the equation shown below. So basically, the contribution of drill shaft is sort of as being one that helping to reduce the driving force due to the arching effect. So basically, when you put a rigid inclusion into the slope with the appropriately spacing in between the drill shaft, when the soil mass tends to slide down, then the arching will develop. And the arching is the one that transfers the soil-to-soil stress into the stress applied to the drill shaft. So with that idea in mind, then your factor safety can be computed as the one shown in this equation, so that driving force is reduced due to the arching effect from the spaced drill shaft. So that's the UASLOPE approach. So now the important question here is, how do you assess or quantify the arching effect? So to do that, we have the previous research, which includes not only the numerical simulations, but prototype field validation work, so that we can kind of fine-tune and validate the finite element approach. So once the three-dimensional finite element simulation technique is validated, then we run a series of simulations for a variety of cases. So now you can see on the right-hand side we have three-dimensional finite element mesh. You can see on the upper right picture where we show a slice of the slope with two drill shafts spaced. And you can see we cut the section, vertical section, right on the upslope side of the drill shaft. And on the lower right diagram, you can see we also can look at the downslope vertical section on the drill shaft. So the finite element simulation is using the strength reduction method to reduce the soil strength until the slope becomes incipient for sliding. So actually, basically, it's at a stage of large abrupt movement where we define the failure curve. At that moment, we can then calculate the stresses. You can see the upper left diagram, which is the plane view of the drill shaft space. And finite element will give you the stress distribution. Here we look at the horizontal stress. And on the left lower diagram, you can see there's a vertical section diagram where you can see the stress distribution on the upslope side of the drill shaft and stress distribution on the downslope side of the drill shaft. So then we can compute the resultant force going from the top of the drill shaft to the slip surface and covering the spacing. So that's the force in that volume. What you have is the resultant force calculated called the force upslope. Then you do the same thing for all the stresses on the downslope side of the drill shaft, and the resultant force is called F downslope. So you can see because of the arching, because the soil in between the drill shaft will move more than the soil behind the drill shaft, where the relative movement of the soil particles resulted in the arching effect. So the stress behind the drill shaft is higher than the stress in the soil in between the drill shaft. So part of the stress is now transferred to the to behind the drill shaft, and that's what we call arching. And this has been validated in the field measurement work where we have a real size drill shaft and load it on the slope with some dead weight, and we can measure the deflection and soil movement and stresses. So this phenomenon is very well documented, not only in the numerical simulation result, but also in the field large-scale load testing result. So the task right now is to try to develop some kind of empirical relation for this eta to relate this, what we call the load transfer factor, to some of the relevant parameters in the problem. And to do that, we have rely on the finite element simulation techniques, because we can cover a wide range of conditions like slope geometry, slope height, soil properties, dimension of the drill shaft, spacing of the drill shaft, and location of the drill shaft on the slope. So any possible design scenario can be investigated by the numerical simulation. So once we have sufficient data base for numerical simulation for computing eta, then we can develop empirical equation for eta, which then can be implemented into UASLOPE program to account for the contribution of the arching effect in reducing the driving force. So the important point here is that eta, the arching, needs to have soil move large enough so that the arching can be fully utilized or developed. So typically, the eta factor or load transfer factor is a function of relative soil movement between the soil particles in between the shaft and the soil particles behind the drill shaft. And it usually takes about some centimeters or close to a half an inch of movement to get the smallest eta factor, and then becomes kind of fully mobilized. So the load is reduced a lot once the eta factor is small. So you can see now how do we incorporate this load transfer factor eta. Oh, I did something. There we go. So you can see we use method of slice. And in UASLOPE, basically, we only use force equilibrium to set up the iterative equation. We can modify it if one likes it to satisfy both force equilibrium and moment equilibrium. But we have compared with other methods like modified Bishop and John Booth's method. They are very similar. So if you use the force equilibrium, you can develop the equation like shown here with the iterative equation. Everybody will be familiar with this equation if they know the method of slice. And then how do we take into account the drill shaft arching effect? You can see the lower equation here where you have the eta is used to modify the inter-slice force. So imagine you have a slice, upslope slice, above the drill shaft, and downslope slice below it. Now, if you don't have the drill shaft, then this pi minus 1 would be equal to pi minus 1 pointing downward. So action reaction should be the same. However, if it happens between these two slides, we have this drill shaft, and because the arching, then this inter-slice force will be reduced by a factor of eta. So it's transferred from this inter-slice to this inter-slice face. So the arching effect is very easily accommodated for by introducing this eta factor to modify this particular inter-slice force for the slice immediately downslope of the drill shaft. All the rest of the slides will be used the same equation for computation. So the modification is very minimal. It really depends on the location of the drill shaft and the eta factor. So the question here is, how do we quantify the eta factor that can accommodate all the situations you may encounter for the real-world project? So we have done a significant number of finite element simulations using Abacus program. And the most recent analysis for 2.1 was done by Arash in 2011. That was also part of Ohio DOT project. And we identified important parameters that will affect this eta factor. So you can see in this little table here, we have identified the soil strength parameters C and B being very important. And then for the drill shaft, the spacing, center-to-center spacing S divided by diameter of drill shaft is also very important. And diameter of shaft is D. And then these theta X that represent the location of the drill shaft on the slope. So these 5 parameters are very important. On the other hand, the slope angle beta is not as important as the other 5. But in any event, all these 6 factors are considered in establishing this semi-empirical equation. And you can see the equation is shown at the very bottom of this slide. So now with that a computational algorithm I just demonstrated to you earlier, using the method of slice with the load transfer factor eta incorporated in the slice that immediately be below the drill shaft, we can write a computer program. So the UASLOPE 2.1 is a program that has been used by Ohio DOT and some of the ODOT consultants you can see the interface is very simple. It allows you to provide the geometry of the slope. It also allows you to provide the location of the drill shaft on different places of the slope. Also, you can define the dimension of the drill shaft in terms of diameter and spacing, so that it's just one very simple window-based interface where you can input all the relevant information, and then the computer will then run using the method of slice and to determine the factor safety with or without the drill shaft. So in this particular view graph, you can see that is the case where the drill shaft is put at somewhere the midpoint of the slope or a little bit down at the midpoint of the slope. And you can see it's 2.49. And the other output is important for the design of the drill shaft is the force, the net force applied to the drill shaft above the sea surface. So we can use that force to design the drill shaft using some commercial program like LTAP, because this is a laterally loaded drill shaft. So we can use that computer program to do the structural design of the drill shaft. But this is a very important output that we use in the structural design of the drill shaft. So this is basically been used for some time by Ohio DOT and some of the consultants who happen to work for ODOT or some other consultants who know the existence of the program. So now why do we go into this enhancement work? So after several years of the usage of program, we have identified there are some bugs in the program, and also we want to streamline the design or optimization process so that we can save the engineer time in using the program for design purpose. So here is the scope, a list of scope for the current work. So first thing we want to do is to run additional finite element simulation so that we can cover a wider range of slope conditions and slope properties. In particular, we want to look at the slope that's relatively flat, and want to look at the soil strength that's very low in cohesion. We want to look at a failure surface that's not circular or not curved, but it's a straight line type of a failure plan. And then based on this additional finite element simulation results, we can develop a new empirical equation to quantify the arching effect. And we can also eliminate some of the issues related to the previous equation. And then the other important enhancement is to provide a capability to allow engineers to interface with the Excel file. So engineers who may want to prepare all the input file using Excel, and they can then import that data file directly into UASLOPE program without the need to go into the program interface to re-input all the information. And it would be easier for engineers to develop many design scenarios using the spreadsheet, because they can copy paste all the repeated information, and then they can run all this at once, rather than we have to run one case and then go back to the program using the program interface and retype in all the input data. So this is, from the time-saving point of view, it will be much easier for engineers if they are doing the optimization for the design, because we're trying to find the optimum dimension of the drill shaft, optimum location, and that will result into economic design with adequate factor safety. And the other work that we have done is to allow for automation to change the drill shaft location. So because in the past, you had to specify the shaft location on the slope to run one case. But now you can provide the starting location, ending location, and the increment of that space, and the computer program will run all these cases at once, and you can get all the results at once, so that you can basically save a lot of repeated runs with this option. Lastly, actually, we want to enhance the capability by allowing the engineer to use this program also to design the slope to be stabilized by anchor only, or if in a special case you may want to have a drill shaft and anchor together, you can also design that particular design scenario. So those are the essential tasks included in this current work. So here is just a table of all the parameters that we used in additional 50 new finite element simulations. Again, those simulations take time because you are doing the strength reduction to get to the slope failure with the drill shaft. And so that's it's a tedious incremental work. And then you can see that we try to cover the cohesion to a nominally negligible value. So 0.1 PSF is the one we use. And then the friction angle, 5 degrees. And the slope angle, we go as low as 20 degrees. Location of the drill shaft, usually we know, well, a lot of research and from our experience, we know typically the optimal location is the midpoint of the slope, so a little bit down. So we're kind of focusing on these two locations. Diameter, most often we are 2 to 4 feet, and then spacing is 2 to 4. So those are the selected parameters in running this 50 additional finite element simulations. And here is the new equation shown at the bottom of the slide. The format is very similar, except we take care of some of the singularity points so that we don't run into problems like if you put some number in, you get this head out to be thrown off, or you got the infinite number, or you got a 0. So those are the singular points we avoid in this new equation. And then you can see the new equation matched with the data computed from finite elements, relatively speaking, acceptable, because we cannot have one equation to satisfy all the data points. But as you can see that the R square is about 75%, and the again, the use of this equation certainly involves some modeling error, but I think that kind of comes with the real world situation. You always cannot match all the data points perfectly. Here is the kind of differentiation of the new points with special interest in this slide. You can see those triangular green ones are for the flat slope, and those ones with yellow highlights are the one with this straight line rather than curved failure surface, and small c are the ones with the red square. So you can see those are the special interest points because that has more interest to Ohio DOT, because a lot of cases they involve with will have a relatively flat slope and stress failure surface and the small c. Okay, so with this new eta factor, then we just put into the old program and we modify so that now the new version of the UASLOPE has incorporated this new eta factor in computation. Then I will just touch on a little bit on the method for dealing with anchor. And this is nothing new. All the commercial software program has the capability to include the effect of anchor in enhancing the factor safety of slope. The way we choose to do it is to put an anchor force at the top of the slope on that particular side that the anchor head located. And the rest are just like any other software program. Then we'll carry through this method of size computation. Now, this was, I guess, agreed on by Ohio DOT because there are people apply this anchor force at the base of the slip surface or at the intersection on the interside face, vertical face. But anyway, I think we look at some review of some commercial software. Seems like this is more appropriate way to handle the anchor force. So that's relatively easy. Once you have incorporated that, then the factor safety of the slope can be calculated. Now, the other case is then, what if you want to control the movement of slope while also ensure the factor safety of slope is adequate? Sometimes we want to use the anchor because there's a pretension there and it can help minimize the slope movement. So occasionally, maybe the slope is too large, and you do need to have more than just drill shaft. So you might have situations where you need to use a combination of a drill shaft and an anchor. So the proposed method is somewhat conservative. So here are the assumptions made. So the anchor force together with the drill shaft in improving the factor safety, we only consider the horizontal portion of anchor force, FH, because the vertical component goes into the shaft, although that would increase the normal force at the base, but we ignore that, which is on the safe side. And the anchor force, just like before, will be acting on the midpoint of side surface. And drill shaft would be applied at the edge of the downslope side of the current slide. Another important consideration, which is validated by our finite element analysis, is that the presence of the anchor does not significantly alter the load transfer factor function. So we do not modify the load transfer function even if we have an anchor applied together with the drill shaft. So with this, then we can implement all these assumptions and this into the computer program 2.3. So here's the schematic diagram showing what I mean by putting the drill shaft on the downslope side of the slide. You can see here. And of course, in our design, the anchor is going through the drill shaft if you have a drill shaft. Of course, if you do not have a drill shaft, then you do have a concrete block on the surface to serve as the anchor head reactions. And the spacing of the anchor would be then a multiple number of the spacing of the drill shaft. So it can be one, then that means every drill shaft will accommodate one anchor, or every other drill shaft will accommodate, or every three other drill shafts. So it would be in this way if you use the anchor together with the drill shaft. Okay, the new modified program, we call it 2.3 because in between 2.1 and 2.3, we have an interim version 2.2, which is submitted to ODOT for their review. But 2.3 includes everything that was developed in 2.2. Still using 2.3 to represent the new version of the software program. So the interface, there's some new features here. The first one is now we are now the import export the Excel file. So if you go to File and you go here and this tab here and then hit this, it will bring out the Excel file. Then you can bring that into this program. And also we provide alternatives here we have a drill shaft information. You can calculate drill shaft and the slope factor static without drill shaft, or you can, with the drill shaft, and use the automatic function embedded, or you can define your load transfer function, or you can have anchor together with drill shaft on or off. When it's off means you don't have anchor, you only have drill shaft. So it covers a different combination of possibility in this interface. If you do choose anchor, then it will allow you to input the anchor force, the angle of the anchor, and the spacing of the anchor. And then over here, if you want to have an option to automatically run multiple locations of drill shaft, then you can say auto put on, then allow you to put the starting point of the drill shaft and the ending point of the drill shaft, so the X min and X maximum, and the increment of the distance between the drill shaft. So in this example, you can just start 20, and then next one will be 30, and 40, 50, so on and so forth. The computer will run all these cases in one computer run, and then provide those output into the output file. So it becomes very convenient for engineers to look at the influence of location of the drill shaft on your design. Okay, so the rest are similar. You define the stitch surface location, you define the pool water pressure in terms of groundwater table or pneumatic surface, or pool pressure ratio. All these are typical in a commercial software program. You define the soil properties, the different soil layers, with this window here, and geometry of the soil profile defined by the vertical sections. So you say, this vertical section, I define this point, this point, this point. It defines the beginning point of the soil layer, and come to here, you can define this point, this point, this point, and so on and so forth. So soil layer geometry would be defined very easily through this interface as well. And also we have to input the crest location and toe location, so that's provided here. So again, this is a very simple interface, and allow you to do multiple runs on different locations of the drill shaft. You can have different design scenarios with or without drill shaft, with drill shaft and anchor or without anchor. So all these are covered by choosing different buttons here. And here is a look at the spreadsheet. This is a developed template, and so you will then use this template to fill in those yellow highlight locations. So you can put a project name here. You can then specify the options that we mentioned here, that use English unit or metric units. Method analysis, effective stress or total stress. We did mention in the report, we recommend to use the effective stress for all the cases, because usually we're dealing with existing slides, so it's a long-term stability issues rather than construction-related issues. Okay, so you can see it's self-explanatory. How to specify the pool pressure, how many vertical section you have, how many soil layers you have, so on and so forth. And then drill shaft information over here, and then soil layer information, and then slope information. So these are kind of allowing engineer to use the same information repeatedly by copy-paste into the spreadsheet, so they can build multiple cases. And they can run this all at once, because this input file, spreadsheet, once you input into the UASLOPE 2.3, it will create an output. And for all the cases that you assemble in the spreadsheet, that will come out with all of them at once. So it saves you a lot of preparation time in preparing your input file. And here's one example showing the output. You can see that this example showing we have an automatic run for multiple positions of drill shaft. So start at the 20 meters offset from the crest of the slope, and to 100 meters, and each 10 feet, you will find new positions. And this is a table of the result that's important, factor safety with the drill shaft. And on this particular example, I think it's 4 feet diameter, S over D is equal to 4. Factor safety as a function of the location, and the shaft, when the drill shaft is placed at different location, and you can plot it. And you can see that typically if we have a target factor safety to achieve is 1.5, then this design will not meet the 1.5 factor safety. Then you have to change the diameter or the spacing so that you rerun it, making sure that you can achieve your target or desirable factor safety. And if you choose this one as a design, then the force applied to the drill shaft as computed is 120 kips. And you can use that force in the LTAP analysis for the structural design of the drill shaft. So you can see the output is geared towards the engineer making judgment in terms of optimizing the dimension of the drill shaft, location of the drill shaft, and eventually you can also look at the structural design, and I guess eventually the ultimate decision would be economy with all the feasible design combinations and which one will be lowest in construction cost. Okay, so as far as the design recommendation for the drill shaft, it's conveniently to use L-pile to do the structural analysis of the drill shaft subjected to the horizontal load. So the length of the drill shaft is typically designed to make sure it has sufficient socket into firm soil, whether it's rock or it's very, very firm soil below the steep surface. And also, of course, we want to satisfy the factor safety with this drill shaft in place or with drill shaft and anchors. And we want to making sure we choose the combination of the size of drill shaft and the length of drill shaft such that the total cost will be minimum. So we not only satisfy the safety concerns as well as the serviceability concerns, but also we're trying to economize the design. Because the constructability issues and the access to the site, that's also need to be considered. Okay, here's some of the conservative approach. I think Ohio DOT agreed to disagree with our recommendation, but that's okay. I think this is very conservative, and you can take the load, apply to the L-pile, and come up with the moment of shear for your structure design. And I think L-pile is just a tool, and how do you model it? I guess each engineer probably would play different, use it in somewhat different way. But I think the force computed from the metal slide is a useful value to design for your drill shaft. And of course, those force is on factor force. So you do the FD design, you have to apply the appropriate load factor into the force come out from the UASLOPE 2.3 program. Okay, so here I very quickly go through an example. Well, this is a very simple-minded example. And here is a 2-layer slope system, and we use the program to identify the critical failure surface with the factor safety 1.05. So this is a slope that is on verge of failure. Right? So now we want to use this slope problem to design the drill shaft to improve the factor safety to a desirable factor safety, whether you use 1.3 or 1.5, that's your agency's call. But anyway, so this is not the real soil slope, just a demonstration purpose. A groundwater table, as you can see here, is right at the boundary between the red soil and the yellow soil. Okay, so using UASLOPE 2.3, one of the output is the relationship between the factor safety and the location of the drill shaft. We call it offset. So that's the distance from the crest of the slope, horizontal distance. And then you can see we try different combination of the shaft dimension from 2 feet to 4 feet, and the spacing versus diameter, this normalized spacing from 2 to 4. So you can see the factor safety as computed for different location, for different shaft dimension and spacing are shown in this diagram. So you can see that if we choose 1.5 as design factor safety, we can see some of the combination will not satisfy the requirement. So those curves below that 1.5 horizontal line will not be adequate. So those points that provide a factor safety above 1.5 would be what we call the feasible design. And then you can take those and to see which one of those combinations will give you the smallest construction cost. And the other output from the computer program is the force applied to the shaft for the same combination of the drill shaft and location we look at in the previous slide. Okay, so those are the output from the UASLOPE 2.3 that will be used as an input in the LTAP analysis for structural design of the drill shaft. So here's the case where we put an anchor, 200 kips anchor force with the anchor angle 25 degrees. And this is the force that you come up with. So the next slide gives you a summary of a feasible design, showing here case 1 to 8, and the diameter and the center-to-center spacing, normalizes diameter, and the computed factor safety. So you can see most of them, except for the last one, close to 1.5, all of them are greater than 1.5. And these two columns gives you the force on the drill shaft. So one of the advantages or benefits, you will call it, of using anchor is that it significantly reduces the force onto the shaft compared to the one without the anchor. Okay. But you take those force, then you can apply it to the drill shaft as a load, so that F net is distributed as a triangular distributed stress, and the anchor, whether it's at the top or some distance below the top, you can put the anchor force at that point of application and run the whole structure analysis by LTAP, from which you can get the moment and shear. You can even look at the diffraction. So here's the typical output of the calculated diffraction. These two curves showing the one with the anchor. So with the anchor force, it pulls the drill shaft upslope. And these two curves showing the one without the anchors. Okay. So this is the example showing that with LTAP, you can compute the diffraction of the drill shaft under that design condition. Here is the moment, so you can take those moments, design the reinforcement for the drill shaft. Similarly, you have distribution of the shear force. This is moment for another case. You can see the distribution of the moment for the drill shaft with or without anchor changes. The pattern and the magnitude changes. So again, the introduction of the anchor under the drill shaft suddenly modifies the magnitude and the distribution pattern of the moment. And similarly, shear force as well. So you take the shear force and the moment, and then design for the reinforcement for the for the drill shaft. And the diffraction usually also can or cannot be the important consideration depending on the applications. If a structures like bridges nearby the slope stabilized by this technique, you certainly want to minimize the amount of diffraction on the slope with the installation of drill shaft. So you need to design your drill shaft so that the diffraction will satisfy the structure requirement. But if purely for the slope stabilization without any relevant structures or pavement nearby, then you probably don't have to worry too much about the diffraction of the drill shaft. But anyway, the tool of LTAP will allow you to consider both the serviceability and the strength limit of the drill shaft under the load coming from the arching effect. Okay, so design strategy actually should be satisfy the geotechnical factor safety of the slope, reinforced with the drill shaft. The drill shaft itself needs to be constructed, so constructability issues needs to be considered. And then for structure design, we're looking at both service limit and the strength limit. Finally, the cost comparison. Okay, so I'm getting to the end of my presentation. I just want to mention some other versions of UASLOPE that's out there, and one is UASLOPE 3.0, which is actually a program sponsored by Ohio DOT, and this is modifying of UASLOPE 2.2 or 2.1 so that it becomes a probabilistic analysis. So we are able to take into account of the soil parameter variability and model errors like the arching effect, the eta effect, that we know it doesn't match the straight line perfectly. So this was already finished, and you can find the report, and there's a state job number indicated here. And if you are interested in using this program because you are interested in looking at the probabilistic approach, is available either through ODOT or you can contact me. The other thing is we have demonstrated the use of UASLOPE for design of drill shaft in a seismic active areas. Because when you do have earthquake produce inertial force on slope. And maybe the design is more of what's the displacement, permanent displacement of slope after the earthquake has occurred. And also certainly the strength limit and all this strength limit and service limit are also of concern. So this one was published in 2014 in the Journal of Soil Dynamics and Earthquake Engineering. So the algorithm and the computer program is available for anybody who's interested in using this for slope stabilization using drill shaft in a seismic active zone. And also the program is very easily adaptable for multiple roles of the drill shaft. And that's being implemented and published by Lin Lee and myself in 2013. So those are additional versions of program in case you have a special need for it. You can look for those references and to address that kind of situation. So as a summary, I guess we have accomplished the task of modifying existing UASLOPE 2.1 so that we would have a new semi-empirical equation for the arching effect. We have implemented the interface so that the input information can be prepared using Excel file so that multiple design scenarios can be done in one shot and then put into the program, and the output will be done in one shot. So you don't have to read on the program one case by one case. we introduced the one-click optimization strategy in finding out the optimum location of drill shaft. Of course, a lot of times maybe the location of drill shaft is dictated by the location and accessibility, but we know usually the optimum location usually is near the midpoint of slope if that's, you know, accessible and easy to construct. And all this data now can be saved into a file for a future references. Okay, and additional capabilities to consider the anchor and also drill shaft with anchor are also introduced. So these are the, I guess, the aspects of the modification on the UASLOPE program. Now the last slide, okay, here is just saying that this can be used for optimization of the design. So optimization means we want to find a combination of location, the size of the drill shaft, and the spacing, whether we need to use anchor or not, if we use anchor, what kind of spacing and orientation or alignment of the anchor with respect to horizontal direction, that's called anchor angle. Those can be optimized because this is an iterative computer program. Okay, now this program certainly can further improve. In the very beginning, we hold the philosophy that this program will be used for fixing a slope that is suffering a failure. So there is always a pre-existing slip surface in a slope, but we entertain the use of drill shaft, so that we do not have that search routine for the critical slip surface, because that will be input as known. The other thing is, I know in some part of the world, the landslide is very, very huge. A big amount of soil volume involved, and sometimes one may contemplate the use of the drill shaft not in a single row, but as a staggered configuration, or even you can put up the alignment of slope as an arch rather than a straight line. So thus, we have done some study. It looks like it's actually beneficial if you do staggered arrangement, or if you put in the arch direction. Well, there are some questions by some of the industry people, as well as the assumptions of the intersite force, because now we only satisfy the force equilibrium. And people say, why don't you satisfy both moment and force equilibrium? Why do we have to assume the direction of the intersite force? Why don't you just use Morgenstern and Price method to allow it to vary with the size? So this could be a possibility if you so insist on, but as we have done some comparisons, I don't think those assumptions really make the program deviate too much from those satisfy all the equilibrium requirements, and with the intersite force to be varied with location. And the other thing, as pointed out by some of the users, is they would like to see that to take into account those stratigraphic uncertainties, because when we deal with the slope, we have a limited number of boreholes, and from that we interpret the soil profile for the slope. And that's one guess out of some possibilities, so the factor set you get from that soil profile may not be safe. And actually we were pointed out by some of the industry people saying that would be because they actually compare our publications case with their computer programs side by side, and then we find out their results different from ours because they are searching the slip surface. We identify and input as a slip surface, But if the search slip surface may be different from the one we identified, and that will cause some discrepancy between the calculated factor safety and the and that gives us an idea. Okay, yeah, soil profile, real rational representation of soil profile is based on the engineer judgment, and that may or may not be representation of the true soil profile. And that's always one of the shortcomings of dealing with anything that we cannot see below the ground surface. So those are some of the possibilities for any feature enhancement. So I would like to acknowledge all the technical guidance and technical support from the ODOT Office of Geotechnical Engineering, and they are listed over here. And certainly, welcome. I have Katie Knight in there, but it didn't show.
Oh, okay.
Sorry about that. But actually, I want to acknowledge all the support from the Office of Research as well in the over years, and particularly supporting this implementation project. So with that, I guess I conclude my presentation, and thank you so much.
Okay, so I will go ahead. I'm going to open up the floor for questions if anybody has any questions. I'm also going to unmute everybody on the phone, so if you do have a question, you can go ahead and you can ask at this point.
So C cannot be zero still, is that correct?
It can be zero now.
It can be
zero. The equation now can be zero. It's just my finite element can never succeed with C equal to 0. I cannot get converged. So the smallest I can put in is 0.2 PSF. Yeah.
Question, Dr. Lee.
Yes,
So
Peter.
The addition of the anchor force.
Yeah.
I understand, the anchor force by itself, but when you're looking at both the anchor force and the drill shaft,
Yeah.
are you assuming that the anchor is the head of the anchor is on the top of the drill shaft?
No, it can be different depths. Yeah. Well, the example I show is at the top, but it can be at different depths along the length of the shaft.
So then the anchor force is being applied to the splice.
Yeah.
But you also have the contribution of the drill shaft.
Yes.
I guess the few times I've tried to model it, I just assume that anchor force is just providing structural support to the drill shaft. And
Yeah.
not really doing anything to the soil. Aren't you kind of, by looking at it the way you are, aren't you including the force of the anchor twice?
Well, I didn't mention, but actually no. The inclusion of the anchor doesn't change the fact of safety. We didn't take into account of that, but it does change the force, internal force in the drill shaft. Is that what you're getting at? What you're saying is that anchor. Yeah, we basically ignored the contributing effect of the anchor in enhancing the factor safety. There is some, but I have a table showing the anchor with, without anchor. You can see the factor safety is the same. I didn't change the factor safety. We purposely, we put it there in calculation, but in output we're simply still using the one that without the anchor. So what you're saying here is that we know the contribution of the anchor when it's used in combination with drill shaft in enhancing the factor safety of the slope. But in our actual output, we ignore that part of contribution to be on the safe side. So it's very conservative. Yeah. So actually, anchor is helping to reduce the structural force in the drill shaft and also to minimize the diffraction of the slope.
So it's supporting the drill shaft.
Yeah.
I mean, providing support to the drill shaft,
Yeah.
which I understand.
Yeah. Yeah. So what it does enhance the factor safety, but if we didn't show that result. So it's kind of conservative in terms of factor safety. But in terms of structural design, we do consider that.
The force at the anchor head is being applied through the drill to the drill shaft.
Yeah.
I have difficulty understanding how that force is being transmitted to the
soil.
flight,
Yeah.
other than through the drill shaft itself.
Right. That's why we don't take into account that. Yeah. There are horizontal force component of the anchor, which then would transmit it to the soil to some extent. Vertical force definitely goes into the shaft and goes into the soil.
So the fact that the anchor is pulling on the drill shaft and kind of pushing the drill shaft again.
Yeah, for the upslope. Right? Yeah. So you can see the deflection of the shaft is actually moving upslope with the anchoring slope. Yeah.
Okay, any other questions? Okay, well with that, we'll go ahead and we'll conclude everything. Again, probably by Monday afternoon, you should be able to view this on the research website. Everything will be linked up there, and if you have any other questions that you think of later, just email them to the research office, and we will get a hold of Dr. Liang and get your questions answered. So thank you all, and have a good day.